Hello class, this week we're going to be talking about color, so it's time we finally talk about color profiles. When we've been creating new documents, we've been setting the color profile to Working RGB sRGB IEC 6 1966 version 2.1, and then we've been leaving it at that. But it's time to get into what that is and what's going on. If we go to Edit, we can see that we have Sign Color Profile and Color Settings. If we click on Color Settings, we can see that we have a working space and an RGB mode. We have sRGB IEC 6 1966 2.1. We also have a working space for CMYK, gray, and spot. We'll talk about those later when we get into print. For now, we're just going to concentrate on sRGB. Now, there are a few other things going on here. We have color management policies, and we'll be talking about that again when we go to print. For the most part, we just need to take note that we preserve the embedded profiles when we're in RGB. Now, this is the default behavior. I haven't changed anything in here. It just does what it needs to do. The conversion options are using the Adobe engine, and its intent is relative chromatic, but it does have different intents. And if you click on this, it will actually tell you about it, but we need to come back to this once we understand a little bit more about things like color gamma and the profiles and what's going on with that. So let me go ahead and close this up. Now I say gamma, we're really going to talk about gamut rather than gamma right now. Gamma will probably come up a little bit later. One other thing, if we go over to Edit, you'll notice we also have a Sign Profile. And if we click that, you can see that we have the working profile, but we can assign it a specific profile of whatever we want to, and this will be stored with the document when we save it. So if we assign it sRGB IEC 6 1966 version 2.1 and tell it OK, when we save this document, file, save as, let's maybe pop this into week 8 demo and then call this color demo. That profile will be stored with it, and we can set it to any profile. We can also convert profile, which is the safer way. Remember when it had the Adobe Ace engine? If we went to convert profile, we have the ability to change these out to different types of profiles. Now, in this case, this won't make any sense right now because we haven't talked about what these profiles are. But we'll revisit this again later when we do the print. For the most part, we're not going to be converting to it, but we'll talk more about what the relative chromatic, perpetual saturation, and absolute chromatic means when we get into the print section of it. Sufficient to say it's different ways to map one set of colors to another set of colors and how we're doing that. So let's get into what I mean by map one set of colors to another set of colors. Well, what is all of that? What's going on there? If you'll recall from our Colorful Notions BBC video that we watched forever ago, or if you did not watch it and instead read the Wikipedia articles, the human eye in general is capable of picking up short, medium, and long waves of light and distinguishing them apart by using our sensors known as cones, if you recall, and I believe rods if we're looking at low light vision. So the short wavelengths are generally referred to by us as blue, the medium are green, and the long are red, and there's a lot of overlap between them. So generally, humans have the ability to pick these up and detect them. But there's also a question about the projectors that are being used. Let's say, for example, you had built a device that was capable of projecting color of various wavelengths out to a viewer, and you called this device a television, and then you could draw things in it and it would project out. Now let's say that somebody else saw that great device and thought, hey, that's pretty cool, I think I'll go ahead and build my own version of that, and I will also project out different colors at different light wavelengths, and that will allow us to see and express all sorts of beautiful images. It'll be absolutely amazing. Now, how do we know that an image that ends up being recorded for television, for example, if we placed a little smiley face in front of it, how do we know that the color that's displayed on one monitor will look the same when displayed on another monitor? Well, we could do things like measure the output of light and determine what's going on, and that's pretty useful. But do we want to do that for every single monitor that we have? Or do we want to be able to say with some degree of certainty that if, for example, we recorded something in yellow on our real life recorded system, how do we know with some degree of certainty that it will be the same yellow on both television monitors when it comes back out? Well, the engineers would need to come up with a way of standardizing things. They'd have to have a way of measuring light in general, saying how bright a certain kind of light is and how well it can reproduce certain kinds of light. And so essentially you'd have to profile what they're capable of reproducing and about how they reproduce it. Now, I keep saying IEC 6, 1966, like it's something that is real and not just a bunch of made-up numbers. Well, there's a reason for that. Over 100 years ago, there was an International Commission on Illumination. Now, that would be ICI in English, but in French, which is appropriate since they met in France, it is actually CIE. Now, these were a bunch of physicists that sat down and said, how do you measure color in a way that makes sense? And so they started coming up with these color space diagrams. And this is the CIE 1931 color space diagram, and you'll actually see these a lot. Let me bring one up for you real quick. Here are some iPhones, and these are some older iPhones, the iPhone 5 and the iPhone 4. And there's something called sRGB. And then it has several diagrams in this weird horseshoe shape again that's going in on it. So let's work our way up to what this horseshoe shape is and what the whole International Commission on Illumination we're up to and what that has to do with color profiles. So here we can see fairly straightforward 3 icons, one for the iPhone 5, one for the old iPhone 4S, and one for sRGB. So here is a square, and that one corresponds with the sRGB. Here is a triangle, and that one will correspond with the iPhone 4S. And here is the iPhone 5, and that one is the little circle, and it's going in here. So what are these? Well, it's saying what colors can be represented on the screen of the different phones as compared to a generic sRGB device. So let's roll back one more time and ask what an sRGB device is. While the Commission on Illumination handled color in general to figure out all of these profiles and how to talk about it, once that was all sorted out, eventually we needed a way to implement it on computer monitors. And so we created more accurately, Hewlett-Packard and Microsoft created in 1996 one of those profiles to use, and they called this sRGB. All right, so here's this weird horseshoe shape again. And here's all kinds of stuff, D65, infinity. What are all these degrees in Kelvin? What's going on? It's the same thing. Well, hold on. So if these are supposed to represent different screens, it seems as though we've got more blue in the old iPhone 4, but we don't have as much green. Is that what it's saying? Well, let's break this down and talk about it a little bit at a time. And it gets a little weird because of these numbers here, this little horseshoe shape that's coming along. Let's go ahead and bring up in Photoshop again, and we'll just hide these 2 documents. And let's talk about representing the universe. So if I come on in and I were to, say, grab a pen, let's say that I wanted to talk about color that humans can experience. What if I wanted to talk about all color first? Because humans experience a subset of color. We can't see infrared or ultraviolet. Some plants have ultraviolet colors, though, and insects can see those, but we can't necessarily see them. We can see a little bit of them, but not very much. All right, so let's say that we did a cube. Remember that cube way back when on Colorful Notions where they were plotting those different lengths of light between the three positions? And so they would do something where they'd say that the short, medium, and long wavelengths would be in three different places, and then that allowed them to build that cube, and then they slid out those glass plates on those cubes, and then they placed little color swatches, and then let them build up this big colorful blob inside of a cube, and then they could reference it to figure out where things were. They were essentially doing the same thing that the International Commission on Illumination, the International Commission on Illumination, were doing. They were trying to figure out how to map stuff. So let's break this down into some smaller pieces. Let's say that we had all of the color in the universe. And I'm just going to represent it with a big blob. And I'm just going to grab a gradient tool. And I'm going to grab a big old circle. And I'm going to get a rainbow. Why not? So here's all the color in the universe. All right. Let's say that this is just it. This is all the color that exists. Now, this is being created on all kinds of, from all kinds of stars out in the universe. It's producing all this electromagnetic radiation. And within that electromagnetic radiation is a small part that mammals and reptiles and amphibians and whatever else on Earth with eyes can witness and see as color. And on one side, you'd end up with infrared. I should really have that down at the bottom. There we go. And then on the other side, you'd have ultraviolet. I'm really messing up this scheme. There we are. So you have ultraviolet, which ends up just before it falls out of the visible color spectrum. On the other side, we have infrared. So if you guys are interested in physics, you may have gone over this before. The electromagnetic spectrum has all kinds of amazing stuff on it, but right now we're focusing on color. So let's say we have the whole universe worth of color. Great. So there it all is. So that brings up a new question. Coming in here, what are we able to see? Well, what is actually producible by the sun, essentially? So this would be everything, right? So out of everything, let's get a subsection of that. Now we're kind of in a weird territory because we're in 3 dimensions instead of just 2, but we're drawing it in 2 dimensions, so it's going to look a little funky. Let's say that we have, we draw. So if it were in 2 dimensions, we would just draw it like that, right? Just a little square. If it's in 3 dimensions, we need to kind of curve it so it's going along the position, and then we'd have to label that third axis. Kind of strange, but hey, that's one way to do it. So let's go ahead and break that down. Let's say that this is now like everything that can be seen in general, right? Everything that we as humans could see. Now, this would require the power of a sun to reproduce, right? Because the sun is producing all of this light. We'd need something of about equivalent. That sounds really expensive. Have you guys ever had a sun in your living room? I think we would probably burn up most of the planet if we were to do something along those lines. So instead, we're going to have to deal with something a little bit smaller than this, right? Some kind of illumination that can be produced by, say, a television or a monitor or anything along those. So we need to talk about this subsection of light that we could potentially see. So if we have all light that is existing by the sun in here, and then we have the whole visible spectrum of light in here, we have an even smaller subsection of light that could be reproduced by something like a television or a phone or a Game Boy or any of those things, something with a monitor, right? Some projector, even your screen at a theater. We have a subsection of a subsection, essentially. So we have all the light in the universe right here. Then we have all the light that a human being could generally see based off of those 3 cones that we have in our eyes. And then we have a smaller section of what we can probably reproduce with a computer monitor or a television or a cellular phone or any of those things. All right, so what would this look like if it wasn't drawn, really fast and goofy looking inside of Photoshop? It looks something like this. Boom. Behold, this is a chromatic diagram for color space. So we have all of the light in the universe. We have a subsection of light that human beings can see, and it's curved all funny because it's trying to represent a z-axis. If we have the y-axis going up and down, the x-axis side to side, we have a z-axis going across. So they'll represent it by bending it with this weird horseshoe, and there we go. So we need to demonstrate this mathematically so that it can be measured. And the first thing you need to do in order to generate something is to have some source of light, right? Because otherwise you're not generating anything. And they call that usually the D15 or D65 point. And I actually cannot remember for certain if the D stands for default or if it stands for daylight, but it's basically the white point. And that is generated mathematically rather than anything else, and it's a way of measuring how white it is. So welcome back to the Wikipedia. Here's the white point. A white point, often referred to as reference white or target white in technical documents, is a set of, and I'm going to mispronounce this, Tristomolius values or chromatically coordinates and chromaticity coordinates, which again is just our beautiful horseshoe shape that we have, that serve to define the color white in an image, capture, encoding, or reproduction. Oh, well, that's interesting, isn't it? That sounds kind of like the color profiles I keep dancing around. Depending on the application, different definitions of white are needed to give acceptable results. For example, photographs taken indoors may be lit by incandescent lights, remember these light bulbs, which are relatively orange compared to daylight. Defining white as daylight will give unacceptable results when attempting to color correct a photograph taken with incandescent lighting. What? Well, it means this. So let's say that, thanks to color constancy, when we go into an incandescently lit room, we don't see it as orange. We see it as a normal room. Our brains have compensated for that. The camera does not have a brain and will not compensate for that in general. So if we were to take a photo without any special compensation settings built in, it will show us all of this weird orange color. Now, if we did a bunch of lab effects on it so that it would, normally be brighter, have better color or whatever, but we designed those effects around photos that we took in daylight, and we applied it to photos that were taken indoors with incandescent light, it would look wrong. And the reason is that it's actually orange inside. The light is not right. So we end up with this D65 as a number built to talk about it. So we measure it out and we say, hey, if you could produce something along these lines, some amount of illumination, and they will have specifically what is required for that because they sat down and they engineered all of this out, then we'll be able to determine based off of that supposedly white light, or as close as you can get it, how much color you can produce, hopefully. And if you were to switch between, say, an orange light and white light as your base white color light, then it will be able to hopefully set everything correctly and transpose it. So in other words, all those effects that we built for daylight applied to orange light will work if you can recalculate the white light correctly. Whew, all right, so this is a lot of information being dropped in on everything, and there's actually quite a bit more, but let's just talk about a little bit more, and we'll do that in the next video because we're coming up to the 20-minute mark here, well, closer and closer to it, and I kind of want to keep these videos short enough for watching. So what we've talked about so far is we need a white point of light in order to start figuring out how to map things. Now, once we've got that, we need to talk about what these little zones that we're making represent and how we're able to implement those. See you in the next video.